Welcome, stargazers, to tonight's journey into the cosmos. Tonight, we're not just looking up at the familiar stars. We're venturing far beyond to the realm of exoplanets, planets orbiting distant suns. Our focus? Their atmospheres. These gaseous envelopes, often vastly different from our own, hold clues to a planet's past, present, and even its potential for life. Imagine skies painted with colors we can scarcely conceive, and storms raging in absolute silence, unheard in the vacuum of space. Let's begin our descent into the fascinating field of exoplanetary atmospheric science. To start, let's consider what an atmosphere actually is. Simply put, it's a layer of gas or layers of gases that surround a planet or other celestial body, held in place by gravity. Earth's atmosphere, composed primarily of nitrogen and oxygen, is our lifeline, providing the air we breathe, shielding us from harmful radiation and regulating our planet's temperature. But exoplanet atmospheres can be wildly different. Their composition, density, and temperature depend on a multitude of factors, including the planet's size, mass, distance from its star, and its geological history. One of the primary ways we study these distant atmospheres is through a technique called transmission spectroscopy. When an exoplanet passes in front of its star, a tiny fraction of the star's light filters through the planet's atmosphere. By analyzing the wavelengths of light that are absorbed or scattered by the atmospheric gases, we can identify the elements and molecules present. It's like looking at a cosmic fingerprint unique to each planet. Imagine a giant, Jupiter-like planet orbiting incredibly close to its star, a hot Jupiter, as astronomers call them. These planets are tidally locked, meaning one side always faces the star, while the other remains in perpetual darkness. The temperature difference between these two sides can be extreme, leading to supersonic winds that whip around the planet, redistributing heat. These winds can carry exotic molecules like titanium oxide, which absorbs blue light, potentially giving the day side of the planet a hazy orange glow. Now, consider a smaller, rocky planet, perhaps similar in size to Earth. If this planet is close enough to its star, it might be subjected to intense stellar radiation. This radiation can strip away the planet's atmosphere over time, especially if the planet lacks a strong magnetic field to deflect the charged particles from the star. This is what happened to Mars. Once a potentially habitable world with a thicker atmosphere and liquid water on its surface, Mars gradually lost its atmosphere to space, leaving behind the cold, dry desert we see today. But what about planets that retain their atmospheres? What kind of exotic chemistry might be taking place? On some exoplanets, we might find clouds made not of water, but of silicate particles, essentially clouds of sand. On others, we might find rain made of molten iron or oceans of liquid methane. The possibilities are truly mind-boggling. The James Webb Space Telescope, with its unprecedented infrared capabilities, is revolutionizing our ability to study exoplanet atmospheres. It can detect the faint signals of molecules like water vapor, carbon dioxide, and methane, which are key indicators of a planet's potential for habitability. By studying the abundance of these molecules, We can learn about the planet's temperature, pressure, and overall chemical composition. One of the most exciting areas of exoplanet research is the search for biosignatures, signs of life in a planet's atmosphere. For example, the presence of oxygen and methane in Earth's atmosphere is largely due to biological activity. However, it's important to note that these molecules can also be produced by non-biological processes, so we need to be cautious when interpreting these signals. Finding a combination of biosignatures that cannot be explained by any known abiotic process would be strong evidence for the existence of life on another planet. Let's delve deeper into the dynamics of exoplanet atmospheres. Imagine a gas giant planet with bands of different colored clouds, similar to Jupiter. These bands are caused by differences in temperature and composition at different latitudes. Strong winds, driven by the planet's rotation and the temperature gradient between the equator and the poles, create powerful jet streams that flow around the planet. These jet streams can transport heat and momentum, influencing the planet's overall climate. On some exoplanets, we might find superrotating atmospheres, where the winds at the equator are much faster than the planet's rotation rate. This phenomenon is not fully understood, but it may be related to the way the planet absorbs and redistributes energy from its star. Superrotating atmospheres can have a significant impact on the planet's temperature distribution, potentially making the planet more habitable than it would otherwise be. Consider the case of HD 189733b, a hot Jupiter exoplanet located about 63 light-years from Earth. This planet has been extensively studied, and we have learned a great deal about its atmosphere. It's a scorching world, with a temperature of over 1,000 degrees Celsius. The winds on HD 189733b are incredibly strong, reaching speeds of up to 8,600 kilometers per hour. And intriguingly, scientists have detected evidence of silicate particles in its atmosphere, suggesting that it might rain glass sideways on this alien world. Another fascinating exoplanet is Kepler 186f, a rocky planet orbiting a red dwarf star about 500 light-years from Earth. Kepler 186f is located in its star's habitable zone, meaning it could potentially have liquid water on its surface. However, because it orbits a red dwarf star, it is likely tidally locked, with one side always facing the star and the other in perpetual darkness. This could lead to extreme temperature differences between the two sides of the planet, potentially affecting its habitability. The nature of its atmosphere is still unknown, but scientists are eager to study it further to determine whether it could support life. Let's now ponder the effects of stellar activity on exoplanet atmospheres. Stars, especially young, active stars, emit powerful flares and coronal mass ejections, bursts of energy and particles that can have a significant impact on the atmospheres of nearby planets. These events can strip away atmospheric gases, heat up the upper atmosphere, and even trigger chemical reactions. Planets orbiting active stars may need to have strong magnetic fields and thick atmospheres to protect themselves from these harmful effects. Consider the potential for atmospheric escape. Atmospheric escape is the process by which gases in a planet's atmosphere leak into space. This can happen through a variety of mechanisms, including thermal escape, where gas molecules gain enough energy to overcome the planet's gravity, and non-thermal escape, where other processes, such as interactions with stellar wind particles, knock gas molecules out of the atmosphere. The rate of atmospheric escape depends on the planet's size, mass, temperature, and the composition of its atmosphere. Now, let's delve into the topic of clouds on exoplanets. Clouds play a crucial role in regulating a planet's temperature and climate. They reflect incoming sunlight back into space, cooling the planet, and they trap outgoing infrared radiation, warming the planet. The composition, altitude, and coverage of clouds can have a significant impact on a planet's habitability. On Earth, clouds are primarily made of water droplets or ice crystals. But on exoplanets, clouds could be made of a variety of exotic substances, such as silicate particles, ammonia ice, or even sulfur compounds. Let's explore the concept of haze in exoplanet atmospheres. Haze is a suspension of tiny particles in the atmosphere that can scatter light and obscure the view of the planet's surface. Haze can be formed by a variety of processes, including photochemical reactions, where sunlight breaks down molecules in the atmosphere, and condensation of gases into solid particles. Haze can have a significant impact on a planet's temperature and climate, and it can also affect our ability to study the planet's atmosphere. Consider the implications for habitability. The presence of a stable, long-lived atmosphere is crucial for a planet to be habitable. The atmosphere provides a buffer against extreme temperature changes, protects the surface from harmful radiation, and can provide the necessary ingredients for life. However, not all atmospheres are conducive to life. A runaway greenhouse effect, like the one that occurred on Venus, can lead to extremely high surface temperatures and make a planet uninhabitable. Similarly, a planet with a very thin atmosphere may be too cold to support liquid water on its surface. The delicate balance of factors that determines whether a planet is habitable is still not fully understood. Let's discuss the role of aerosols in exoplanet atmospheres. Aerosols are tiny particles suspended in the atmosphere that can affect the way light is absorbed and scattered. They can be made of a variety of substances, including dust, salt, and organic compounds. Aerosols can be produced by natural processes, such as volcanic eruptions and dust storms, or by human activities, such as burning fossil fuels. They can have a significant impact on a planet's temperature and climate, and they can also affect our ability to study the planet's atmosphere. Now, let's think about the potential for lightning on exoplanets. Lightning is a dramatic display of electrical discharge that can occur in atmospheres with strong convective activity. It can be triggered by collisions between ice crystals and clouds, or by the separation of charge in dust storms. Lightning can produce a variety of chemical compounds, including ozone and nitrogen oxides, which can affect the composition of the atmosphere. The presence of lightning on an exoplanet could be an indicator of a dynamic and active atmosphere. Consider the possibilities for aurorae on exoplanets. Aurorae, also known as the northern and southern lights, are shimmering displays of light that occur in the upper atmosphere when charged particles from the star interact with the planet's magnetic field. These particles excite atoms and molecules in the atmosphere, causing them to emit light. The color of the aurora depends on the type of atom or molecule that is excited. Aurorae are most commonly seen near the poles, where the magnetic field lines converge. The presence of aurorae on an exoplanet could be an indicator of a strong magnetic field, which can protect the planet from harmful stellar radiation. Let's explore the concept of atmospheric tides on exoplanets. Atmospheric tides are periodic variations in atmosphere pressure and wind that are caused by the gravitational pull of the star or other planets. These tides can be significant, especially on planets that are close to their star. They can affect the planet's temperature distribution and climate, and they can also influence the planet's rotation rate. The study of atmospheric tides can provide valuable insights into the structure and dynamics of exoplanet atmospheres. Now, let's discuss the search for water vapor in exoplanet atmospheres. Water is essential for life as we know it, so the presence of water vapor in an exoplanet's atmosphere is a promising sign. Water vapor can be detected through transmission spectroscopy by looking for absorption features in the infrared spectrum. However, it's important to note that water vapor can also be produced by non-biological processes, such as volcanic activity. Therefore, the detection of water vapor alone is not sufficient evidence for the existence of life. But it does make a planet a more interesting target for further investigation. Consider the challenges of studying exoplanet atmospheres. Exoplanets are incredibly faint and distant, making them difficult to observe. Their atmospheres are even fainter and more difficult to study. We rely on sophisticated techniques such as transmission spectroscopy and high-resolution spectroscopy to tease out the faint signals from these distant worlds. We also need to account for the effects of the Earth's atmosphere and the instruments we use to make the observations. Despite these challenges, we have made remarkable progress in recent years, and we are continuing to develop new and innovative techniques to study exoplanet atmospheres. Let's think about the future of exoplanet atmospheric science. The James Webb Space Telescope is already providing us with unprecedented views of exoplanet atmospheres. In the coming years, we can expect to see even more powerful telescopes, both in space and on the ground, that will allow us to study exoplanet atmospheres in even greater detail. We will be able to probe the composition, temperature, and dynamics of these atmospheres with unprecedented precision. We will also be able to search for biosignatures, signs of life, in the atmospheres of potentially habitable exoplanets. The future of exoplanet atmospheric science is bright, and we can look forward to many exciting discoveries in the years to come. Imagine the possibilities of finding a planet with an atmosphere similar to Earth's. A planet with a breathable atmosphere, liquid water on its surface, and a stable climate. Such a planet would be a prime candidate for colonization, or at least for further exploration. While we're still far from finding such a planet, the search is on, and we're making progress every day. Consider the ethical implications of searching for life on other planets. If we were to find evidence of life on another planet, what would be our responsibility? Will we have the right to interfere with that life, or should we leave it alone? These are complex questions with no easy answers, but it is important to start thinking about them now before we actually find life on another planet. Let's delve deeper into the concept of atmospheric stability. An atmosphere is said to be stable if it resists vertical motion. In a stable atmosphere, air parcels that are displaced upward will tend to sink back down to their original level, and air parcels that are displaced downward will tend to rise back up. Atmospheric stability is determined by the temperature profile of the atmosphere. If the temperature decreases rapidly with altitude, the atmosphere is unstable. If the temperature decreases slowly with altitude, or even increases with altitude, the atmosphere is stable. Atmospheric stability has a significant impact on weather patterns and climate. Now, let's discuss the role of greenhouse gases in exoplanet atmospheres. Greenhouse gases are gases that absorb and emit infrared radiation, trapping heat in the atmosphere. The most important greenhouse gases on Earth are water vapor, carbon dioxide, and methane. These gases play a crucial role in regulating Earth's temperature, making it habitable. However, too much greenhouse gas can lead to a runaway greenhouse effect, like the one that occurred on Venus. The study of greenhouse gases in exoplanet atmospheres can provide valuable insights into the planet's temperature and climate. Consider the potential for terraforming exoplanets. Terraforming is the process of modifying a planet's atmosphere, temperature, surface topography, and ecology to be similar to Earth's environment, so as to make it habitable by humans. This is a long-term and complex process that would require significant technological advancements. However, it is not entirely impossible. If we were to find a planet that is otherwise suitable for life but lacks a breathable atmosphere, terraforming could be a way to make it habitable. Let's explore the concept of atmospheric superrotation. Atmospheric superrotation is a phenomenon in which the atmosphere of a planet rotates faster than the planet itself. This is observed on Venus, where the atmosphere rotates about 60 times faster than the planet. The mechanism that drives atmospheric superrotation is not fully understood, but it is thought to be related to the way the planet absorbs and redistributes energy from the sun. Atmospheric superrotation can have a significant impact on the planet's temperature distribution and climate. Now, let's think about the potential for life in the clouds of exoplanets. On Earth, there are microorganisms that live in clouds, feeding on organic compounds and water. It is possible that similar organisms could exist in the clouds of exoplanets. The clouds of exoplanets could provide a relatively stable environment with access to water, sunlight, and organic compounds. The search for life in the clouds of exoplanets is a challenging but potentially rewarding endeavor. Consider the role of magnetic fields in protecting exoplanet atmospheres. A planet's magnetic field can deflect charged particles from the star, protecting the atmosphere from being stripped away. Planets with strong magnetic fields are more likely to retain their atmospheres over long periods of time. The strength of a planet's magnetic field depends on its size, rotation rate, and the presence of a liquid metallic core. The study of magnetic fields in exoplanets can provide valuable insights into the planet's internal structure and its ability to retain its atmosphere. Let's discuss the concept of atmospheric collapse. Atmospheric collapse is a phenomenon in which a planet's atmosphere freezes out onto the surface, forming a layer of ice. This can happen if the planet's temperature drops below the freezing point of the atmospheric gases. Atmospheric collapse can lead to a dramatic change in the planet's climate, making it uninhabitable. It is thought that atmospheric collapse may have occurred on Mars in the past. Now, let's explore the potential for finding technosignatures in exoplanet atmospheres. Technosignatures are signs of technology that could be detected in the atmospheres of exoplanets. These could include artificial gases, such as chlorofluorocarbons, CFCs, or signs of large-scale engineering projects, such as solar power collectors. The search for technosignatures is a long shot, but it is not impossible. If we were to find a technosignature in the atmosphere of an exoplanet, it would be strong evidence for the existence of intelligent life. Consider the ethical implications of contacting extraterrestrial civilizations. If we were to detect a technosignature and establish contact with an extraterrestrial civilization, what would be our responsibility? Will we have the right to share our knowledge and technology with them, or should we leave them alone? These are complex questions with no easy answers, but it is important to start thinking about them now, before we actually make contact. Let's delve deeper into the concept of atmospheric escape mechanisms. There are several different mechanisms by which gases can escape from a planet's atmosphere. Thermal escape occurs when gas molecules gain enough energy from heat to overcome the planet's gravity. Non-thermal escape mechanisms include photoionization, where gas molecules are ionized by ultraviolet radiation from the star, and sputtering, where gas molecules are knocked out of the atmosphere by collisions with energetic particles from a star. The rate of atmospheric escape depends on the planet's size, mass, temperature, and the composition of its atmosphere. Now, let's discuss the role of volcanoes in shaping exoplanet atmospheres. Volcanoes can release large amounts of gas and dust into the atmosphere, which can have a significant impact on the planet's climate. Volcanic eruptions can also create new landforms and alter the surface of the planet. The study of volcanoes on exoplanets can provide valuable insights into the planet's geological history and its potential for habitability. Consider the potential for panspermia, the idea that life can spread from one planet to another via meteoroids or other means. If life exists on one planet in a star system, it is possible that it could spread to other planets in the same system. This could happen if a large impact event ejects rocks from the surface of the planet into space. Some of these rocks could contain microorganisms that could survive the journey through space and land on another planet. If the conditions on the new planet are favorable, the microorganisms could colonize the planet and start a new life. Panspermia is a controversial idea, but it is not entirely impossible. Let's explore the concept of exomoons, moons orbiting exoplanets. Exomoons are thought to be common, but they are difficult to detect because they are small and faint. However, if we were to find an exomoon with a thick atmosphere, it could be a potentially habitable world. Exomoons could provide a stable environment with access to water, sunlight, and organic compounds. The search for exomoons is a challenging but potentially rewarding endeavor. Now, let's think about the potential for finding life on rogue planets. Planets that have been ejected from their star systems and are wandering through space. Rogue planets may seem like unlikely candidates for life, but they could potentially have subsurface oceans that are kept warm by geothermal activity. These oceans could provide a stable environment for life, even in the absence of sunlight. The search for life on rogue planets is a long shot, but it is not impossible. Consider the challenges of communicating with extraterrestrial civilizations. If we were to establish contact with an extraterrestrial civilization, how would we communicate with them? We would need to develop a universal language that could be understood by both civilizations. This would be a difficult task, but it is not impossible. Scientists have already developed several potential universal languages based on mathematics and physics. The challenge is to find a way to transmit these languages across vast distances of space. Let's delve deeper into the concept of atmospheric inversions. An atmospheric inversion is a situation in which the temperature increases with altitude rather than decreasing as it normally does. Atmospheric inversions can trap pollutants near the surface, leading to poor air quality. They can also affect weather patterns and climate. Atmospheric inversions are common in cities, where they're caused by the release of heat from buildings and vehicles. Now, let's discuss the role of dust storms in exoplanet atmospheres. Dust storms are common on Mars, and they can have a significant impact on the planet's climate. Dust storms can block sunlight, cooling the surface and warming the atmosphere. They can also transport dust particles around the planet, spreading them over large areas. The study of dust storms on exoplanets can provide valuable insights into the planet's climate and its potential for habitability. Consider the potential for finding life in subsurface oceans on exoplanets. Many exoplanets are thought to have subsurface oceans, which are kept warm by geothermal activity. These oceans could provide a stable environment for life, even in the absence of sunlight. On Earth, there are microorganisms that live in subsurface oceans, feeding on chemicals released from hydrothermal vents. It is possible that similar organisms could exist in the subsurface oceans of exoplanets. The search for life in subsurface oceans is a challenging but potentially rewarding endeavor. Let's explore the concept of snowball Earth, a period in Earth's history when the entire planet was covered in ice. Snowball Earth events are thought to have occurred several times in Earth's history. They were caused by a decrease in greenhouse gases, which led to a cooling of the planet. The ice cover reflected sunlight back into space, further cooling the planet. Snowball Earth events are thought to have been ended by volcanic eruptions, which released large amounts of greenhouse gases into the atmosphere. Now, let's think about the potential for finding life on planets orbiting white dwarf stars. White dwarf stars are the remnants of stars that have exhausted their nuclear fuel. They are small and faint, but they can still host planets. Planets orbiting white dwarf stars would be subjected to intense radiation but they could potentially have subsurface oceans that are shielded from the radiation. The search for life on planets orbiting white dwarf stars is a long shot, but it is not impossible. Consider the challenges of traveling to exoplanets. Exoplanets are incredibly distant, making it difficult to travel to them. The fastest spacecraft we have today would take thousands of years to reach the nearest exoplanet. However, scientists are working on developing new technologies that could make interstellar travel possible. These include fusion rockets, which would use nuclear fusion to generate thrust, and warp drives, which would bend space-time to allow spacecraft to travel faster than the speed of light. Interstellar travel is still a long way off, but it is not impossible. Let's delve deeper into the concept of atmospheric rivers. Atmospheric rivers are long, narrow bands of concentrated water vapor in the atmosphere. They are responsible for a significant portion of the precipitation in some regions. Atmospheric rivers can cause heavy rainfall and flooding, but they can also be beneficial, providing water for agriculture and other uses. The study of atmospheric rivers on exoplanets can provide valuable insights into the planet's climate and its potential for habitability. Now, let's discuss the role of wildfires in shaping exoplanet atmospheres. Wildfires can release large amounts of smoke and ash into the atmosphere, which can have a significant impact on the planet's climate. Wildfires can also alter the surface of the planet, changing the vegetation and the soil. The study of wildfires on exoplanets can provide valuable insights into the planet's environment and its potential for habitability. Consider the potential for finding life in extreme environments on exoplanets. On Earth, there are microorganisms that live in extreme environments, such as hot springs, acidic lakes, and deep-sea vents. These organisms are called extremophiles, and they have adapted to survive in conditions that would be lethal to most other organisms. It is possible that similar organisms could exist in extreme environments on exoplanets. The search for life in extreme environments is a challenging but potentially rewarding endeavor. Let's explore the concept of the faint young sun paradox. The faint young sun paradox is the observation that the sun was much fainter in the early history of the solar system than it is today. However, the Earth was still warm enough to support liquid water on its surface. This is a paradox because the Earth should have been frozen solid if the sun was as faint as it is thought to have been. Scientists have proposed several solutions to the faint young sun paradox, including a thicker atmosphere with more greenhouse gases or a different distribution of continents. Now, let's think about the potential for finding life on planets orbiting binary stars. Binary stars are systems of two stars that orbit each other. Planets orbiting binary stars would be subjected to complex gravitational forces and varying amounts of radiation. However, it is still possible for planets to exist in stable orbits around binary stars. The search for life on planets orbiting binary stars is a challenging but potentially rewarding endeavor. Consider the challenges of detecting exoplanet atmospheres. Exoplanet atmospheres are incredibly faint and difficult to detect. They are also very diverse, with a wide range of compositions, temperatures, and pressures. Scientists use a variety of techniques to detect exoplanet atmospheres, including transmission spectroscopy, emission spectroscopy, and phase curve analysis. Each of these techniques has its own strengths and weaknesses, and they're often used in combination to get a more complete picture of the atmosphere. Let's delve deeper into the concept of atmospheric escape velocity. Atmospheric escape velocity is the minimum speed that an object needs to escape from a planet's atmosphere. The escape velocity depends on a planet's mass and radius. The higher the escape velocity, the more difficult it is for gases to escape from the atmosphere. Planets with high escape velocities are more likely to retain their atmospheres over long periods of time. Now, let's discuss the role of impact events in shaping exoplanet atmospheres. Impact events can release large amounts of energy into the atmosphere, which can have a significant impact on the planet's climate. Impact events can also eject material from the planet's surface into space, which can then spread to other planets. The study of impact events on exoplanets can provide valuable insights into the planet's history and its potential for habitability. Consider, too, the fascinating possibility of exoplanets with global oceans and how this might affect their atmospheres. A planet entirely covered in water would have a very different climate than a planet with continents. The oceans would act as a massive heat reservoir, moderating temperature swings and potentially leading to a more stable and uniform global climate. Water vapor, a potent greenhouse gas, would be abundant in the atmosphere, influencing the planet's overall energy balance. Furthermore, the interaction between the ocean and the atmosphere would create complex weather patterns, potentially leading to persistent cloud cover and unique atmospheric circulation. Imagine the constant evaporation and condensation cycles, the formation of colossal oceanic storms, and the way these processes would shape the chemical composition of the atmosphere. Let's now explore the concept of atmospheric tides on exoplanets. Just as the moon's gravity causes tides on Earth's oceans, the gravity of a star can cause tides in an exoplanet's atmosphere. These atmospheric tides can be particularly strong on planets that are very close to their star, or on planets with very massive atmospheres. Atmospheric tides can cause significant temperature variations across the planet's surface, and they can also affect the planet's atmospheric circulation patterns. The interplay between gravitational forces and atmospheric dynamics creates a fascinating area of study, revealing how celestial mechanics can directly influence the weather on distant worlds. Think about the potential for detecting biosignatures in exoplanet atmospheres. Biosignatures are indicators of life, such as specific gases that are produced by living organisms. The detection of biosignatures in an exoplanet atmosphere would be a major breakthrough in the search for extraterrestrial life. However, it is important to note that biosignatures can also be produced by non-biological processes, so it is crucial to carefully consider all possible explanations before concluding that life has been detected. Some promising biosignatures include oxygen, methane, and phosphine, but their presence must be interpreted within the context of the planet's overall environment. The search for biosignatures is a complex and challenging endeavor, but the potential reward is immense. Now, let's turn our attention to the role of stellar activity in shaping exoplanet atmospheres. Stars, including our own sun, are not static objects. They emit a constant stream of charged particles known as stellar wind and occasionally erupt with powerful flares and coronal mass ejections. These events can have a significant impact on the atmospheres of orbiting exoplanets, particularly those close to their star. The high-energy radiation and particles can erode the atmosphere, stripping away gases and potentially altering its chemical composition. The strength of the stellar wind and the frequency of flares can vary greatly from star to star, leading to diverse atmospheric conditions on different exoplanets. Understanding stellar activity is crucial for assessing the habitability of exoplanets. Finally, let's consider the long-term evolution of exoplanet atmospheres. Atmospheres are not static entities. They evolve over time due to a variety of factors, including volcanic activity, weathering, and interactions with a planet's interior and the space environment. The loss of an atmosphere can transform a potentially habitable planet into a barren wasteland, while the accumulation of greenhouse gases can lead to runaway warming. Understanding the processes that drive atmospheric evolution is essential for predicting the long-term fate of exoplanets and their potential for harboring life. Studying the atmospheres of exoplanets is like looking into a time machine, allowing us to glimpse the past, present, and future of these distant worlds. The interplay between a planet's atmosphere and its surface is also a key area of research. For instance, volcanic outgassing can replenish atmospheric gases, while weathering processes can remove them. Imagine a planet riddled with active volcanoes, constantly spewing gases like carbon dioxide and sulfur dioxide into the atmosphere. This could lead to a thick, dense atmosphere and potentially contribute to a runaway greenhouse effect. On the other hand, if a planet has extensive oceans and land masses, chemical weathering of rocks can draw down carbon dioxide from the atmosphere, potentially leading to a cooler climate. The balance between these processes is crucial for determining the long-term stability and habitability of a planet. Another fascinating aspect of exoplanet atmospheres is the presence of clouds and hazes. On Earth, clouds play a vital role in regulating temperature and precipitation. Similarly, clouds and hazes on exoplanets can significantly affect their climate. These clouds can be composed of various substances, depending on the planet's temperature and atmosphere composition. For instance, on cooler exoplanets, clouds might be made of water ice or ammonia ice, while on hotter exoplanets, they could be composed of silicates or even metallic compounds. The presence and properties of clouds can influence the amount of starlight reflected back into space, the distribution of heat across the planet, and the overall atmospheric circulation patterns. Observing and characterizing clouds on exoplanets is a challenging but crucial step in understanding their climate and habitability. Furthermore, the study of exoplanet atmospheres provides insights into the planet's formation history. The composition of an atmosphere can reveal clues about the building blocks that formed the planet and the processes that shaped its early evolution. For example, the ratio of different isotopes of elements like carbon and oxygen can provide information about the origin of the planet's water and other volatile compounds. By comparing the atmospheric compositions of different exoplanets, we can gain a better understanding of the diversity of planetary systems and the factors that influence planet formation. It's like piecing together a cosmic puzzle, where each exoplanet atmosphere provides a piece of the puzzle. The techniques used to study exoplanet atmospheres are constantly evolving. Transmission spectroscopy, which involves analyzing the starlight that passes through a planet's atmosphere, has been a workhorse in this field. However, new techniques are being developed to directly image exoplanets and analyze the light reflected from their atmospheres. These direct imaging techniques hold immense promise for characterizing the atmospheres of fainter and more distant exoplanets. As technology advances, we can expect to learn even more about the composition, structure, and dynamics of exoplanet atmospheres. And finally, it's important to remember that the search for life beyond Earth is a marathon, not a sprint. The study of exoplanet atmospheres is a complex and iterative process. We may encounter false positives and dead ends along the way. However, with each new observation and each new discovery, we move closer to answering the fundamental question: are we alone in the universe? The potential reward, the discovery of life beyond Earth, is worth the effort. So, as you drift off to sleep tonight, imagine the possibilities that await us in the vast expanse of the cosmos. Imagine the alien skies, the silent storms, and the potential for life on distant worlds. The universe is full of wonders, and we are only just beginning to explore them. The future of exoplanet atmospheric research is brimming with possibilities, driven by ambitious new missions and technological leaps. Telescopes like the James Webb Space Telescope, JWST, are already revolutionizing our ability to probe exoplanet atmospheres with unprecedented detail. JWST's infrared capabilities allow us to detect a wider range of molecules, including biosignatures, potential indicators of life. Future missions, currently in the planning stages, aim to build upon JWST's success, potentially offering even greater sensitivity and resolution for studying these distant worlds. Imagine a telescope specifically designed to block out the light from a star, revealing the faint glow of a planet orbiting it. Such a feat would enable direct imaging of Earth-like exoplanets and a thorough analysis of their atmospheric compositions. Beyond space-based observatories, ground-based telescopes are also playing a crucial role in exoplanet atmospheric research. Extremely large telescopes, YLTs, with their massive mirrors, will gather enormous amounts of light, enabling detailed studies of exoplanet atmospheres from the ground. These telescopes will complement space-based missions, providing a comprehensive view of exoplanets across a wide range of wavelengths. The synergy between space and ground-based observations is crucial for a holistic understanding of these alien worlds. One of the most exciting prospects in exoplanet atmospheric research is the search for biosignatures. While the presence of a single molecule is unlikely to be definitive proof of life, The detection of a combination of molecules in specific ratios could be a strong indicator. For instance, the simultaneous presence of methane and oxygen in an atmosphere that is not in chemical equilibrium could suggest biological activity. However, it's crucial to consider abiotic sources of these molecules as well. Volcanic activity or photochemical reactions could produce similar signatures. Therefore, a comprehensive understanding of the planet's environment, including its geology, climate, and stellar radiation, is essential for interpreting potential biosignatures. The study of exoplanet atmospheres also provides valuable insights into the habitability of planets. A planet's atmosphere plays a crucial role in regulating its temperature, shielding it from harmful radiation and distributing heat around the globe. The presence of greenhouse gases, such as carbon dioxide and water vapor, can trap heat and make a planet warmer. However, too many greenhouse gases can lead to a runaway greenhouse effect, as seen on Venus, where the surface temperature is hot enough to melt lead. Understanding the delicate balance of factors that determine a planet's habitability is crucial for identifying potentially habitable exoplanets. Furthermore, studying the atmospheric dynamics of exoplanets can reveal clues about their climates and weather patterns. Just as we study weather patterns on Earth to understand our own climate, we can use similar techniques to study the atmospheres of exoplanets. By observing how clouds form, how winds circulate, and how temperatures vary across a planet's surface, we can gain a better understanding of its climate and its potential to support life. Imagine mapping the cloud cover of a distant exoplanet and discovering giant storms raging across its surface, far more powerful than anything we experience on Earth. These discoveries can help us understand the diversity of climates in the universe and the factors that influence planetary habitability. The quest to understand exoplanet atmospheres is not just about finding life beyond Earth. It's also about understanding our place in the universe. By studying these distant worlds, we can learn more about the processes that shape planets and the conditions that make life possible. We can also gain a deeper appreciation for the uniqueness and fragility of our own planet. As we continue to explore the cosmos, we may find that Earth is not the only place where life can thrive. Or we may discover that Earth is a rare and precious oasis in a vast and barren universe. Either way, the journey of discovery will be filled with wonder and excitement. So, close your eyes and imagine the possibilities. Imagine the discoveries that await us as we continue to explore the alien skies and silent storms of distant worlds. The universe is vast and mysterious, and we are only just beginning to unravel its secrets. Sweet dreams. And as we refine our techniques and build more powerful telescopes, we'll be able to probe even deeper into the atmospheres of exoplanets, searching for biosignatures, telltale signs of life. These biosignatures could be anything from specific combinations of gases in the atmosphere that are unlikely to occur naturally, to the presence of organic molecules that are building blocks of life. The search for biosignatures is a challenging but incredibly exciting endeavor that could potentially answer one of the biggest questions in science. Are we alone in the universe? Think about the possibilities. Imagine finding an exoplanet with an atmosphere rich in oxygen, but with levels of methane that can only be explained by biological activity. Or perhaps discovering an atmosphere with traces of chlorofluorocarbons, compounds that are not known to occur naturally and are typically associated with industrial processes. These kinds of discoveries would be groundbreaking and would revolutionize our understanding of life in the universe. However, it's important to remember that the search for biosignatures is not without its challenges. We need to be careful not to jump to conclusions based on limited data. There are many non-biological processes that can produce gases and molecules that might mimic biosignatures. For example, volcanic activity can release large amounts of methane and sulfur dioxide into the atmosphere, which could potentially be mistaken for signs of life. Therefore, we need to carefully consider all possible explanations before concluding that we have found evidence of life on an exoplanet. Beyond the search for life, studying exoplanet atmospheres can also teach us about the diversity of planetary systems and the processes that shape them. By comparing the atmospheres of different exoplanets, we can learn about the factors that influence their composition, temperature, and climate. We can also gain insights into the formation and evolution of planetary systems, including our own. For instance, some exoplanets have atmospheres that are much hotter and denser than Earth's, while others have atmospheres that are much cooler and thinner. Some exoplanets have atmospheres that are dominated by hydrogen and helium, while others have atmospheres that are rich in heavier elements like carbon and oxygen. By studying these differences, we can learn about the processes that determine the composition of planetary atmospheres and the factors that influence their evolution over time. The study of exoplanet atmospheres is a rapidly evolving field, with new discoveries being made all the time. As we continue to explore the cosmos, we are sure to find even more amazing and surprising exoplanets, each with its own unique atmosphere and its own story to tell. And with each new discovery, we will gain a deeper understanding of the universe and our place within it. So, let your mind wander through the cosmos, drifting among these distant worlds, each with its own unique atmospheric symphony. Allow the gentle whispers of scientific discovery to lull you into a peaceful slumber, knowing that the quest to understand these alien skies is ongoing, and the universe continues to unveil its secrets, one exoplanet at a time. Sleep well, and as you drift off, consider the incredible technological advancements that make these discoveries possible. Telescopes like the James Webb Space Telescope, with its unparalleled infrared capabilities, are revolutionizing our ability to probe exoplanet atmospheres. By analyzing the light that passes through or is emitted by these atmospheres, we can identify the unique spectral fingerprints of different molecules. This is akin to shining a light through a prism and observing the resulting rainbow. But instead of colors, we see the absorption and emission patterns of various gases. These patterns tell us what elements and compounds are present, their abundance, and even the temperature and pressure of the atmosphere. The data we collect is incredibly complex, requiring sophisticated computer models and algorithms to interpret. Scientists use these tools to simulate the behavior of exoplanet atmospheres, taking into account factors like stellar radiation, planetary gravity, and chemical reactions. These models help us understand how different processes interact to create the diverse atmospheric conditions we observe. Imagine trying to recreate a miniature version of an alien world inside a computer, simulating its weather patterns, its chemical composition, and its interactions with its host star. It's a monumental task, but one that is yielding incredible insights. Think about the challenges involved in detecting these faint signals from light years away. The light from an exoplanet is often overwhelmed by the much brighter light of its host star. It's like trying to spot a firefly next to a searchlight. Scientists use a variety of techniques to overcome this challenge, including blocking out the starlight with specialized instruments called coronagraphs and star shades. These devices allow us to isolate the light from the exoplanet and analyze it more effectively. The ingenuity and precision required to build and operate these instruments are truly remarkable. Furthermore, consider the implications of studying exoplanet atmospheres for our understanding of climate change. By examining the atmospheres of planets with different compositions and temperatures, we can gain a better understanding of the factors that influence planetary climates. This knowledge can help us improve our climate models and make more accurate predictions about the future of Earth's climate. Studying exoplanet atmospheres is not just about understanding distant worlds. It's also about understanding our own planet and the challenges we face. The quest to understand exoplanet atmospheres is a collaborative effort involving scientists and engineers from around the world. It's a testament to the power of human curiosity and our desire to explore the unknown. As we continue to develop new technologies and techniques, we will undoubtedly uncover even more secrets about these distant worlds. And who knows, perhaps one day we will even find evidence of life beyond Earth, hidden within the swirling clouds and silent storms of an alien atmosphere. Until then, let the mysteries of the cosmos fill your dreams. And may you find peace in the knowledge that the universe is vast and full of wonder. Sleep soundly and dream of alien skies. And speaking of future discoveries, let's consider the exciting possibilities that lie ahead. Future missions, such as the Extremely Large Telescope and the James Webb Space Telescope, are poised to revolutionize our understanding of exoplanet atmospheres. These powerful instruments will allow us to probe exoplanet atmospheres in unprecedented detail, revealing the presence of biosignatures, telltale signs of life. Imagine the moment when we finally detect definitive evidence of life on another planet. It would be a discovery that would change our understanding of our place in the universe forever. But even without finding definitive evidence of life, the study of exoplanet atmospheres is incredibly valuable. By studying the diversity of planetary atmospheres, we can learn more about the processes that shape planetary evolution. We can learn about the conditions that are necessary for a planet to be habitable. And we can even learn about the potential for life to exist in environments that are very different from our own. Think about planets orbiting red dwarf stars, which are much smaller and cooler than our sun. These planets are often tidally locked, meaning that one side of the planet always faces the star, while the other side is in perpetual darkness. What would the atmosphere of such a planet be like? How would the temperature and pressure vary across the planet's surface? Could life exist in such an extreme environment? These are just some of the questions that scientists are trying to answer. The study of exoplanet atmospheres also has implications for our understanding of planetary formation. By studying the chemical composition of exoplanet atmospheres, we can learn about the building blocks that went into forming these planets. We can learn about the role that different elements and molecules play in planetary formation, and we can even learn about the history of the solar system. For example, the presence of certain elements in an exoplanet's atmosphere could indicate that the planet formed in a region of the protoplanetary disk that was rich in those elements. Or, the absence of certain elements could indicate that the planet underwent a period of intense heating or bombardment. And let's not forget the sheer beauty and wonder of exoplanet atmospheres. Imagine gazing upon a planet with swirling clouds of ammonia or methane, or a planet with a permanent aurora that lights up the night sky. These alien landscapes are not just scientifically interesting. They are also incredibly beautiful and inspiring. They remind us that the universe is full of surprises and that there is always more to discover. So as you drift off to sleep tonight, imagine yourself traveling to one of these distant worlds. Imagine what it would be like to stand on the surface of an alien planet, gazing up at an unfamiliar sky. Let the mysteries of the cosmos fill your dreams, and may you find peace in the knowledge that the universe is vast and full of wonder. Sleep soundly and dream of alien skies and silent storms brewing in the atmospheres of faraway worlds. May your rest be deep and your dreams be filled with the wonders of the universe. Good night. And as we consider these alien skies, let's delve a little deeper into the tools and techniques scientists use to unravel their secrets. One of the primary methods is spectroscopy. When starlight passes through an exoplanet's atmosphere, certain wavelengths of light are absorbed by the elements and molecules present. By analyzing the resulting spectrum, the pattern of absorbed and transmitted light, we can identify the chemical fingerprints of the atmosphere's constituents. It's like shining a flashlight through a prism. The light breaks down into its component colors, revealing a unique barcode for each element and compound. The James Webb Space Telescope, or JWST, is a game changer in this field. Its infrared capabilities allow us to peer through the dust clouds that often obscure our view of exoplanets, revealing atmospheric details that were previously inaccessible. JWST can detect the faint signals of water vapor, carbon dioxide, methane, and other molecules, providing invaluable clues about a planet's potential for habitability and even signs of biological activity. Think of it as an incredibly sensitive nose, capable of sniffing out even the faintest whiffs of life on worlds light years away. But interpreting these spectral signatures is not always straightforward. Exoplanet atmospheres are dynamic and complex, influenced by factors such as temperature, pressure, and the presence of clouds. Cloud cover, in particular, can be a significant challenge, as it can obscure the underlying atmospheric layers and distort the spectral signals. Scientists use sophisticated computer models to simulate exoplanet atmospheres, taking into account these various factors to accurately interpret the observed data. It's like trying to solve a complex puzzle where each piece of information, each spectral line, each temperature reading contributes to the overall picture. Beyond chemical composition, scientists are also interested in understanding the dynamics of exoplanet atmospheres. How do winds circulate? Are there jet streams or storm systems? What role does the planet's rotation play in shaping its climate? These are all important questions that can help us understand how exoplanets function as complex systems. For example, some exoplanets have been found to have incredibly strong winds, driven by extreme temperature differences between their day and night sides. These winds can redistribute heat around the planet, influencing its overall climate and potentially affecting its habitability. The study of exoplanet atmospheres is not just about finding other Earths. It's about understanding the incredible diversity of planets that exist in the universe and learning about the fundamental processes that shape their atmospheres and climates. It's about pushing the boundaries of our knowledge and expanding our understanding of our place in the cosmos. And who knows, perhaps one day we will discover a planet with an atmosphere so unique, so unexpected, that it will challenge everything we thought we knew about planetary science. Until then, let us continue to explore these alien skies, to decode their silent storms, and to dream of the wonders that await us in the vast expanse of the universe. Sleep well, and may your dreams be filled with the ethereal glow of distant worlds. The techniques used to probe these alien atmospheres are as varied as the exoplanets themselves. Transmission spectroscopy, as we've discussed, is a powerful tool, but it's just one piece of the puzzle. Another crucial method is emission spectroscopy, which involves studying the thermal radiation emitted by an exoplanet. This allows us to determine the temperature profile of the atmosphere and identify the presence of certain molecules that absorb and re-emit radiation at specific wavelengths. By analyzing the intensity and wavelengths of the emitted light, scientists can infer the composition and temperature structure of the atmosphere, even on the planet's night side. This is particularly useful for hot Jupiters, which are tidally locked and have a permanent day and night side with significant temperature differences. Phase curve analysis is another fascinating technique. As an exoplanet orbits its star, the amount of reflected light we see changes depending on the planet's phase, much like the phases of the moon. By carefully measuring these changes in brightness over time, scientists can create a phase curve that reveals information about the planet's albedo, reflectivity, temperature distribution, and even the presence of clouds. A planet with a uniform temperature distribution will have a smooth, symmetrical phase curve, while a planet with significant temperature variations or patchy cloud cover will have a more complex and asymmetrical phase curve. Direct imaging, although challenging, offers the most direct view of exoplanet atmospheres. This technique involves blocking out the light from the host star to reveal the faint light from the exoplanet itself. Direct imaging allows scientists to obtain spectra and even images of exoplanets, providing a wealth of information about their atmosphere properties. However, direct imaging is only possible for relatively large, bright exoplanets that are far enough away from their host stars to be resolved. Future space telescopes, such as the James Webb Space Telescope, are poised to revolutionize direct imaging, enabling us to study the atmospheres of smaller, cooler exoplanets, potentially including Earth-like worlds. One of the most exciting areas of research in exoplanet atmospheres is the search for biosignatures, signs of life. These are specific molecules or combinations of molecules that are indicative of biological activity. For example, the simultaneous presence of methane and oxygen in an atmosphere would be a strong biosignature, as these gases react with each other and would need to be constantly replenished by a biological source. However, it's important to note that biosignatures can also be produced by non-biological processes, so scientists need to carefully consider all possible explanations before concluding that life is present. Detecting biosignatures is an incredibly difficult task, requiring extremely sensitive instruments and sophisticated data analysis techniques. But the potential reward, the discovery of life beyond Earth, is well worth the effort. The composition of an exoplanet's atmosphere is also intimately linked to its formation and evolution. The building blocks of a planet, the dust and gas in the protoplanetary disk, determine the initial composition of its atmosphere. Over time, the atmosphere can be modified by various processes, such as outgassing from the planet's interior, impact from asteroids and comets, and interactions with the planet star. By studying the atmospheric composition of exoplanets, scientists can gain insights into their formation history and understand how they have evolved over billions of years. For instance, the presence of heavy elements in an exoplanet's atmosphere can indicate that the planet formed further out in the protoplanetary disk, where these elements were more abundant. And as we continue to explore and analyze exoplanet atmospheres, remember the sheer scale of what we're doing. We are, in essence, performing remote sensing on worlds light years away, using the faint signals of light to unravel their secrets. Each new discovery, each new atmospheric profile, each new hint of a possible biosignature brings us closer to answering the fundamental question: are we alone in the universe? The journey is long, the challenges are immense, but the potential rewards are beyond measure. Close your eyes now and imagine yourself drifting among these distant worlds, bathed in the ethereal glow of alien skies. May your dreams be filled with the quiet wonder of cosmic exploration and the silent symphony of distant storms. Good night. Now, let's delve a little deeper into some specific examples of exoplanet atmospheres that have captivated the scientific community. Consider the hot Jupiters, gas giants that orbit incredibly close to their host stars. These planets experience intense stellar radiation, which dramatically influences their atmospheric composition and dynamics. We've observed scorching temperatures reaching thousands of degrees Celsius, leading to the evaporation of elements like iron and magnesium. which then condense into clouds of metallic rain. Imagine skies filled with silicate vapor and storms of molten iron, a truly alien and awe-inspiring spectacle. Then there are the super-Earths, planets larger than our own but smaller than Neptune. These worlds are particularly intriguing because their atmospheres could potentially harbor conditions suitable for liquid water, a key ingredient for life as we know it. Studying their atmospheric composition is crucial for determining whether they possess the necessary elements and conditions to support life. We are looking for the telltale signs of water vapor, carbon dioxide, and other molecules that could indicate a habitable environment. The challenge lies in the diversity of super-Earth atmospheres. Some may be dominated by hydrogen and helium, resembling mini Neptunes, while others might have denser, more Earth-like atmospheres. Unraveling these differences is a key focus of current research. Another fascinating aspect of exoplanet atmospheres is the presence of clouds. Clouds play a crucial role in regulating a planet's temperature and influencing its climate. On Earth, clouds reflect sunlight back into space, helping to cool the planet. They also trap heat, preventing it from escaping into the atmosphere. On exoplanets, clouds can be composed of a wide variety of substances, depending on the planet's temperature and atmospheric composition. We've detected clouds made of silicates, sulfides, and even exotic materials like potassium chloride. The distribution and properties of these clouds can tell us a great deal about the atmospheric dynamics and climate of these distant worlds. Furthermore, the study of exoplanet atmospheres is not just about finding habitable planets or signs of life. It's also about understanding the fundamental processes that shape planetary atmospheres in general. By comparing the atmospheres of different exoplanets, we can gain insights into the factors that determine their composition, temperature, and climate. We can learn about the role of stellar radiation, gravitational forces, and internal heat in shaping planetary atmospheres. This knowledge can then be applied to our own solar system, helping us to better understand the evolution of Earth's atmosphere and the potential for habitability on other planets in our cosmic neighborhood. The techniques used to study exoplanet atmospheres are constantly evolving. One of the most promising methods is transmission spectroscopy, which involves observing the light from a star as it passes through the atmosphere of a planet orbiting that star. As the light travels through the atmosphere, certain wavelengths are absorbed by specific molecules, creating a unique spectral fingerprint that reveals the composition of the atmosphere. Another powerful technique is emission spectroscopy, which involves measuring the light emitted by the planet itself. This light contains information about the temperature and composition of the atmosphere. Future telescopes, such as the Extremely Large Telescope, YELT, and the James Webb Space Telescope, JWST, promise to revolutionize our understanding of exoplanet atmospheres. These powerful instruments will be able to observe exoplanets with unprecedented detail, allowing us to probe their atmospheres with greater precision and sensitivity. We will be able to detect fainter signals, identify new molecules, and study the atmospheric dynamics of exoplanets in greater detail than ever before. The next decade promises to be a golden age of exoplanet research, with the potential for groundbreaking discoveries that will reshape our understanding of the universe and our place within it. So, as you drift off to sleep, consider the vastness of the cosmos and the countless worlds that await our discovery. Imagine the alien skies, the silent storms, and the potential for life beyond Earth. The quest to understand exoplanet atmospheres is a journey of exploration, discovery, and ultimately, a quest to answer the fundamental question: are we alone? Let the wonders of the universe fill your dreams, and may you awaken with a renewed sense of curiosity and awe. Sweet dreams and good night. And as we ponder this profound question, let's delve a little deeper into some of the fascinating aspects of exoplanet atmospheres. Consider, for instance, the concept of atmospheric escape. Over billions of years, planets can lose their atmospheres to space, a process driven by factors like solar radiation and the planet's gravity. Lighter elements, such as hydrogen and helium, are particularly susceptible to this escape. Understanding the rate and mechanisms of atmospheric escape is crucial for determining a planet's long-term habitability. A planet that loses its atmosphere too quickly might become a barren wasteland, unable to support liquid water on its surface. Studying exoplanets with varying masses and distances from their stars allows us to model and predict the fate of planetary atmospheres across the galaxy. Another area of intense interest is the search for biosignatures in exoplanet atmospheres. Biosignatures are molecules that indicate the presence of life. On Earth, for example, oxygen is produced primarily by photosynthesis, and its presence in our atmosphere is a strong indicator of life. However, identifying biosignatures on exoplanets is a complex challenge. We need to consider the possibility of false positives, molecules that could be produced by non-biological processes. For example, volcanic activity or geological processes could release certain gases into the atmosphere. Therefore, scientists are developing sophisticated models and algorithms to distinguish between true biosignatures and false positives. The search for biosignatures is a long shot, but the potential reward, the discovery of life beyond Earth, is immense. Beyond the composition of exoplanet atmospheres, scientists are also interested in their dynamics. Winds, clouds, and storms play a crucial role in shaping the climate of a planet. On Earth, weather patterns are driven by the rotation of the planet, the distribution of land and water, and the energy input from the sun. On exoplanets, these factors can vary dramatically, leading to exotic and unpredictable weather phenomena. Some exoplanets may have global winds that circulate the entire planet, while others may be dominated by massive storms that rage for centuries. By studying the dynamics of exoplanet atmospheres, we can gain a better understanding of the complex interplay between energy, matter, and motion that governs the climate of planets throughout the universe. And as we continue our exploration, it's important to remember that the study of exoplanet atmospheres is a collaborative endeavor, bringing together scientists from diverse fields such as astronomy, physics, chemistry, and biology. Each discipline brings its unique perspective and expertise to the table, allowing us to tackle the complex challenges of understanding these distant worlds. It's a field driven by curiosity, innovation, and a deep-seated desire to unravel the mysteries of the cosmos. It's a journey that will undoubtedly lead to unexpected discoveries and a profound shift in our understanding of our place in the universe. So, close your eyes now and let your imagination soar. Picture swirling clouds of ammonia on a giant gas planet, or the faint glow of a distant sunset on a rocky world orbiting a red dwarf star. Imagine the possibilities, the challenges, and the endless wonders that await us as we continue to explore the vast expanse of the universe. Let the quiet hum of scientific inquiry lull you into a peaceful slumber, knowing that somewhere, scientists are working tirelessly to unlock the secrets of these alien skies. Sleep well, and may your dreams be filled with the beauty and mystery of the cosmos. Good night, and as you drift off, consider the instruments that make these incredible discoveries possible. From ground-based telescopes like the Very Large Telescope in Chile, peering through Earth's atmosphere, to space-based observatories like the James Webb Space Telescope, soaring above it, we are constantly developing new and more powerful tools to probe the secrets of exoplanet atmospheres. Think about the intricate engineering, the complex algorithms, and the sheer ingenuity that goes into designing and building these instruments. They are our eyes and ears on distant worlds, allowing us to analyze the faint light that has traveled trillions of miles across the cosmos, carrying with it the fingerprints of alien atmospheres. The James Webb Space Telescope, in particular, represents a monumental leap forward in our ability to study exoplanets. Its unprecedented infrared sensitivity allows us to see through the hazy atmospheres of many exoplanets, revealing details that were previously hidden from view. We can now detect the presence of key molecules like water vapor, methane, and carbon dioxide with greater precision than ever before, providing valuable clues about the planet's composition, temperature, and potential for habitability. Imagine the excitement of the scientists who first glimpsed these spectral signatures, knowing that they are on the verge of unraveling a new chapter in the story of planetary formation and evolution. But the challenges are immense. Exoplanets are incredibly faint and distant, and their atmospheres are often shrouded in clouds and haze. Separating the light from the exoplanet from the overwhelming glare of its host star is like trying to see a firefly next to a searchlight. Scientists use a variety of techniques to overcome these challenges, including transit spectroscopy, which involves studying the light that passes through the exoplanet's atmosphere as it transits in front of its star, and direct imaging, which involves blocking out the light from the star to directly observe the exoplanet. Each technique has its own strengths and limitations, and researchers are constantly developing new and innovative approaches to improve our ability to study these distant worlds. And what about the future? What are the next big questions that scientists are hoping to answer about exoplanet atmospheres? One of the most exciting areas of research is the search for biosignatures, signs of life, in exoplanet atmospheres. This could involve looking for specific combinations of gases that are unlikely to be produced by non-biological processes, such as the presence of both methane and oxygen in significant quantities. Of course, the detection of a biosignature would not be definitive proof of life, as there could be other, as yet unknown processes that could produce these gases. But it would certainly be a tantalizing hint that we are not alone in the universe. Another important area of research is the study of exoplanet climate. By understanding the dynamics of exoplanet atmospheres, we can begin to predict how these planets will respond to changes in their environment. This is particularly important for planets that are potentially habitable, as even small changes in temperature or atmospheric composition could have a profound impact on their ability to support life. Scientists are developing sophisticated climate models that can simulate the complex interactions between the atmosphere, the oceans, and the land, if there is any, on exoplanets, allowing us to explore a wide range of scenarios and make predictions about the future of these distant worlds. So, as you continue to relax and prepare for sleep, let your mind wander to the possibilities. Think about the vastness of the universe, the sheer number of exoplanets that are waiting to be discovered, and the potential for finding other worlds that are similar to our own. Imagine the day when we finally detect a definitive biosignature in the atmosphere of an exoplanet, confirming that life exists beyond Earth. It's a future that is within our reach, thanks to the tireless efforts of scientists around the world. Let the wonder of it all wash over you as you drift into a peaceful and restful sleep. The universe is vast, and its secrets are waiting to be uncovered. Sweet dreams. And as you ponder these grand questions, consider the very tools and techniques that allow us to peer across such immense distances. It's not just about building bigger and better telescopes, although that is certainly a key part. It's also about developing innovative methods for analyzing the faint light that reaches us from these distant worlds. Think about transit spectroscopy, for example. When an exoplanet passes in front of its star, a tiny fraction of the star's light filters through the planet's atmosphere. By carefully analyzing the spectrum of this light, we can identify the chemical elements and molecules present in the atmosphere. Each element absorbs light at specific wavelengths, creating a unique fingerprint that reveals its presence. This is like shining a light through a prism and seeing the individual colors that make up the white light. Except in this case, the colors tell us about the composition of a distant planet's air. Then there's the technique of direct imaging, where we attempt to directly capture an image of an exoplanet. This is incredibly challenging because the light from the planet is often overwhelmed by the much brighter light of its star. However, by using clever techniques like coronagraphs, which block out the starlight, and adaptive optics, which correct for the blurring effects of Earth's atmosphere, we can sometimes directly image these distant worlds. Direct imaging allows us to study the planet's surface features, if any, and to analyze its atmosphere in even greater detail. But beyond the specific techniques, it's also important to remember the power of collaboration and innovation in scientific research. The study of exoplanet atmospheres is a truly interdisciplinary field, bringing together astronomers, physicists, chemists, and computer scientists from around the world. These researchers are constantly developing new ideas and pushing the boundaries of what is possible, and their collective efforts are driving our understanding of exoplanets forward at an incredible pace. New observatories, both on Earth and in space, are being planned and built, promising even more exciting discoveries in the years to come. As you drift further into slumber, consider the sheer audacity of what we are attempting to do. We are trying to understand the atmospheres of planets that are trillions of miles away, using only the faint light that reaches us across the vastness of space. It's a testament to human curiosity, ingenuity, and our relentless desire to explore the unknown. And with each new discovery, we are not only learning more about exoplanets, but also about our own place in the universe. We are learning about the conditions that make life possible and about the potential for life to exist elsewhere in the cosmos. So, let these thoughts fill your mind as you fall asleep and dream of distant worlds, alien skies, and the endless possibilities that lie beyond our solar system. May your sleep be deep and filled with the wonders of the universe. Good night. And as we contemplate these far-off realms, let's delve a little deeper into the composition of these alien atmospheres. What exactly are we finding when we analyze the light filtering through them? Well, the answer is a complex cocktail of elements and compounds, each telling its own story about the planet's history and potential habitability. We're detecting water vapor, for instance, which is crucial for life as we know it. Its presence suggests the possibility of oceans or lakes on the planet's surface, although it could also exist in the upper atmosphere as clouds or even as a component of a runaway greenhouse effect. Methane is another molecule of great interest. On Earth, much of the methane in our atmosphere is produced by biological activity, so its detection on an exoplanet could be a tantalizing hint of life. However, methane can also be produced by geological processes, so it's important to consider all possible sources before jumping to any conclusions. Carbon dioxide is also frequently detected, and it plays a significant role in regulating a planet's temperature through the greenhouse effect. The amount of carbon dioxide in an exoplanet's atmosphere can tell us about its volcanic activity, its carbon cycle, and its overall climate. Beyond these familiar molecules, we're also finding more exotic compounds, depending on the type of exoplanet we're observing. Some hot Jupiters, for example, have been found to have atmospheres containing titanium oxide, which can absorb light and create temperature inversions, where the upper atmosphere is hotter than the lower atmosphere. This can lead to unusual weather patterns and atmospheric dynamics. We're also detecting silicates, the same materials that make up many of the rocks on Earth, in the atmospheres of some exoplanets. These silicates can form clouds of dust and create hazy skies, obscuring our view of the planet's surface. The presence and abundance of these different molecules can be used to infer the planet's temperature, pressure, and chemical composition. This information, in turn, can help us to understand how the planet formed, how it has evolved over time, and whether it might be capable of supporting life. It's like being a cosmic detective, piecing together clues from the faint light of distant worlds to unravel their mysteries. The study of exoplanet atmospheres is not just about identifying molecules. It's about understanding the complex interplay of physical and chemical processes that shape these alien worlds. And with each new discovery, we get closer to answering the fundamental question: are we alone in the universe? Think about the sheer scale of the challenge. These planets are so far away that even the most powerful telescopes can barely detect them. Yet, we are able to analyze the light that has traveled across vast distances of space and time, extracting information about the composition and dynamics of their atmospheres. It's a remarkable feat of human ingenuity, and it's a testament to the power of science to unlock the secrets of the universe. As you drift off to sleep, remember that the universe is full of wonders waiting to be discovered. There are countless exoplanets out there, each with its own unique atmosphere, climate, and potential for life. And with each passing year, we're getting closer to understanding these distant worlds and our place within the grand cosmic tapestry. Sleep well and dream of the stars. But the story doesn't end with just identifying the components. Understanding the dynamics of these atmospheres is equally crucial. Think of Earth's weather patterns, the intricate dance of winds, pressure systems, and temperature gradients. Exoplanet atmospheres are just as dynamic, perhaps even more so, given the extreme conditions some of these worlds endure. We're talking about planets tidally locked to their stars, with one side perpetually baked in sunlight and the other shrouded in eternal darkness. Imagine the temperature gradients, the pressure differences, the sheer force of the winds that must rage across such a landscape. Scientists are developing sophisticated computer models to simulate these alien weather systems. These models take into account factors like the planet's size, mass, orbital period, and the composition of its atmosphere. By running these simulations, we can begin to predict the types of clouds that might form, the direction and speed of the winds, and the overall climate of the planet. We're even starting to see evidence of jet streams similar to those on Earth, but potentially thousands of times stronger, whipping around these distant worlds at incredible speeds. One of the most fascinating aspects of exoplanet atmospheric dynamics is the possibility of cold traps. These are regions in the atmosphere where temperatures are so low that certain molecules, like water vapor, can freeze out and condense into ice crystals. These ice crystals can then form clouds that reflect sunlight, helping to cool the planet even further. Cold traps could play a crucial role in regulating the temperature of exoplanets, especially those that are relatively close to their stars. And then there are the storms. We've detected evidence of colossal storms on some exoplanets, storms that dwarf anything we've ever seen on Earth. These storms can be driven by a variety of factors, including temperature differences, atmospheric instabilities, and even the planet's magnetic field. Imagine storms that rage for centuries, covering entire hemispheres of a planet. The sheer scale and intensity of these phenomena are mind-boggling. The study of exoplanet atmospheres is also pushing the boundaries of technology. We need increasingly powerful telescopes and innovative techniques to observe these distant worlds. For example, scientists are developing new methods to filter out the glare of the host star, allowing us to see the faint light of the exoplanet more clearly. We're also using sophisticated algorithms to analyze the spectra of exoplanet atmospheres, teasing out the subtle signals that reveal their composition and dynamics. Future missions, like the James Webb Space Telescope, are poised to revolutionize our understanding of exoplanet atmospheres. With its unprecedented sensitivity and resolution, JWST will be able to probe the atmospheres of a wider range of exoplanets, including smaller, rocky planets that are more similar to Earth. This will allow us to search for biosignatures, molecules that are indicative of life in the atmospheres of these distant worlds. The quest to understand exoplanet atmospheres is a long and challenging one, but it's also one of the most exciting and rewarding endeavors in modern science. It's a journey of discovery that is taking us to the very edge of our knowledge, and it's helping us to answer some of the most fundamental questions about our place in the universe. As you close your eyes tonight, consider the vastness of space and the countless worlds that are waiting to be explored. Imagine the alien skies, the silent storms, and the potential for life that may exist on these distant planets. The universe is a place of endless wonder, and we are only just beginning to scratch the surface of its mysteries. Let your mind wander among the stars and drift off to a peaceful sleep, knowing that the adventure of discovery continues. Good night. And as we peer deeper into these alien atmospheres, we're not just learning about their composition and dynamics. We're also gaining crucial insights into the potential habitability of these worlds. The presence of liquid water, a stable climate, and the right chemical ingredients are all vital for life as we know it. By studying exoplanet atmospheres, we can assess the likelihood that these conditions exist on other planets. Think about it. The detection of oxygen, methane, or other biosignatures in an exoplanet's atmosphere could be a game changer, potentially indicating the presence of extraterrestrial life. It's a tantalizing prospect that drives much of the research in this field. But the search for life isn't the only compelling reason to study exoplanet atmospheres. These studies also help us understand the diversity of planetary systems in our galaxy. Each exoplanet is unique, with its own set of characteristics that are shaped by its formation history, its distance from its star, and its interactions with other planets in the system. By studying a wide range of exoplanets, we can begin to piece together a more complete picture of how planetary systems form and evolve. We can learn about the processes that lead to the formation of gas giants like Jupiter, rocky planets like Earth, and everything in between. We can also gain insights into the factors that determine whether a planet will be habitable or not. Consider the example of hot Jupiters, gas giant planets that orbit extremely close to their stars. These planets are subjected to intense radiation and tidal forces, which have a profound impact on their atmospheres. Studying the atmospheres of hot Jupiters can help us understand how these extreme conditions affect planetary evolution. We can learn about the processes that drive atmospheric escape, the loss of atmospheric gases to space. We can also study the complex interactions between the planet's atmosphere and its magnetic field. These studies can provide valuable insights into the behavior of planetary atmospheres in general. And then there are the smaller, rocky planets that are more similar to Earth. These planets are particularly interesting because they are the most likely candidates to harbor life. However, studying the atmospheres of these planets is also more challenging because they are smaller and fainter than gas giants. We need extremely powerful telescopes and innovative techniques to detect and analyze their atmospheres. But the potential payoff is enormous. The detection of biosignatures in the atmosphere of a rocky exoplanet would be one of the most significant discoveries in human history. The field of exoplanet atmospheric science is rapidly evolving, with new discoveries being made all the time. As our technology improves and our understanding deepens, we can expect even more exciting revelations in the years to come. We are living in a golden age of exoplanet research, and the future is bright. So, as you drift off to sleep, remember the incredible journey of discovery that is unfolding around us. Imagine the vastness of space, the diversity of planets, and the potential for life that may exist beyond our solar system. The universe is full of mysteries, and we are just beginning to unravel them. Close your eyes, relax, and let your mind wander among the stars. Sweet dreams. And as you ponder the possibilities, consider the tools we use to unveil these distant atmospheric secrets. Telescopes, both ground-based and spaceborne, are our primary eyes on the exoplanet universe. The Hubble Space Telescope has provided invaluable early data, but newer generations, like the James Webb Space Telescope, are revolutionizing the field. Webb, with its unprecedented infrared capabilities, allows us to probe deeper into exoplanet atmospheres and detect a wider range of molecules. The techniques we employ are equally fascinating. Transit spectroscopy, for example, relies on the subtle dimming of a star's light as an exoplanet passes in front of it. By analyzing the wavelengths of light that are absorbed or scattered during this transit, we can identify the chemical composition of the planet's atmosphere. Different molecules absorb light at different wavelengths, leaving a unique fingerprint that reveals their presence. Imagine shining a beam of light through a prism. The resulting rainbow tells you what colors are present. Transit spectroscopy is similar, but instead of colors, we're looking for the spectral signatures of molecules like water, methane, or carbon dioxide. Another technique, direct imaging, is more challenging but offers a more direct view of exoplanets. It involves blocking out the light from the host star to reveal the faint glow of the planet itself. This allows us to study the planet's atmosphere directly, without relying on transits. Direct imaging is particularly useful for studying planets that are far from their stars, where transits are rare. But the data we collect is only part of the story. We also need sophisticated models to interpret the observations and understand the physical and chemical processes that are shaping exoplanet atmospheres. These models incorporate everything we know about atmospheric physics, chemistry, and radiative transfer. They allow us to simulate the behavior of exoplanet atmospheres under a wide range of conditions and to predict what we might see with future observations. Building these models is incredibly complex, requiring powerful computers and the expertise of scientists from many different disciplines. Think about the sheer scale of the challenge. We're trying to understand the atmospheres of planets that are trillions of miles away, based on tiny amounts of light that have traveled for years, decades, or even centuries. It's like trying to understand the weather on a distant island, based only on the faint glimmers of light you can see from its shores. Yet, with each new observation and each new model, we're getting closer to unlocking the secrets of these alien worlds. The search for biosignatures, indicators of life, is a particularly exciting area of exoplanet atmospheric research. Biosignatures are molecules that are produced by living organisms and that are unlikely to be found in significant quantities in the absence of life. Oxygen, for example, is a potential biosignature because it's constantly being produced by plants through photosynthesis. However, oxygen can also be produced by non-biological processes, so it's important to consider the context in which it's found. Other potential biosignatures include methane, nitrous oxide, and phosphine. The detection of a robust biosignature in the atmosphere of an exoplanet would be a game changer, providing strong evidence that we are not alone in the universe. And beyond biosignatures, there's so much more to learn about exoplanet atmospheres. We want to understand how clouds form on other planets, how winds circulate, and how weather patterns evolve. We want to know how the atmospheres of exoplanets interact with their surfaces and their magnetic fields. We want to understand how planetary atmospheres change over time, and how they are affected by events like stellar flares and asteroid impacts. Each exoplanet atmosphere is a unique laboratory, offering us a chance to test our theories and expand our understanding of planetary science. So, as you close your eyes and prepare for sleep, let your imagination soar to these distant worlds. Picture the swirling clouds of a hot Jupiter, the hazy atmosphere of a super-Earth, or the potentially life-bearing atmosphere of a rocky exoplanet. Think about the incredible ingenuity and dedication of the scientists who are working to unravel these mysteries. And remember that the universe is vast and full of wonders waiting to be discovered. Pleasant dreams, and may your sleep be filled with the quiet rustling of alien winds and the soft glow of distant stars. The cosmos awaits, and as we continue to explore these faraway atmospheric realms, we are constantly refining our tools and techniques. The next generation of telescopes, like the James Webb Space Telescope, are poised to revolutionize exoplanet atmospheric studies. With its unprecedented sensitivity and infrared capabilities, JWST will be able to probe the atmospheres of smaller, cooler exoplanets, including those that are more Earth-like in size and temperature. This will allow us to search for biosignatures with greater precision and to characterize the compositions of exoplanet atmospheres in much greater detail. Beyond JWST, there are also plans for future missions that will be specifically designed to study exoplanet atmospheres. These missions will employ a variety of techniques, including transit spectroscopy, direct imaging, and coronagraphy, to block out the light from the host star and directly observe the faint light reflected or emitted by the exoplanet. These observations will provide us with a wealth of information about the atmospheric composition, temperature, and structure of exoplanets. The challenge of studying exoplanet atmospheres is immense, but the potential rewards are even greater. By understanding the atmospheres of these distant worlds, we can learn more about the processes that shape planetary climates, the conditions that are necessary for life, and the prevalence of habitable planets in the universe. We can also gain insights into the origins and evolution of our own solar system. The study of exoplanet atmospheres is a truly interdisciplinary field, bringing together astronomers, physicists, chemists, and biologists in a common quest to understand our place in the cosmos. Consider for a moment the sheer diversity of exoplanets that have already been discovered. From scorching hot Jupiters orbiting incredibly close to their stars, to icy Neptune-like worlds shrouded in thick clouds, each planet presents a unique set of atmospheric conditions and challenges. There are planets with raging winds that whip around their equators at thousands of miles per hour, and planets with stable, stratified atmospheres that resemble the layers of an onion. Some exoplanets have atmospheres that are rich in water vapor, while others are dominated by carbon dioxide or methane. This incredible variety suggests that there are countless other types of exoplanets waiting to be discovered, each with its own unique atmospheric story to tell. And as we learn more about exoplanet atmospheres, we may even begin to understand the potential for life beyond Earth. While the detection of a definitive biosignature would be a monumental discovery, even the absence of such a signature can provide valuable information. By studying the chemical compositions of exoplanet atmospheres, we can learn about the processes that might prevent life from arising, or that might lead to the development of alternative forms of life that are unlike anything we have ever seen before. So, as you drift off to sleep, imagine yourself as a cosmic explorer, venturing into the unknown depths of space. Picture yourself orbiting a distant star, gazing upon the alien skies of a faraway world. Listen to the subtle sounds of the planetary winds and feel the gentle warmth of the starlight on your face. Let the mysteries of exoplanet atmospheres fill your dreams, and may your slumber be peaceful and restorative. The universe is calling, and tomorrow we will continue our exploration of the cosmos, one exoplanet atmosphere at a time. Sweet dreams, and may your night be filled with the wonder of the stars. And remember, the study of exoplanet atmospheres is not just about understanding distant worlds. It's also about understanding our own. By comparing the atmospheres of exoplanets to the atmosphere of Earth, we can gain insights into the processes that have shaped our planet's climate and environment over billions of years. We can learn about the factors that have made Earth habitable and the threats that could potentially jeopardize its habitability in the future. This comparative approach allows us to place Earth in a broader cosmic context and to appreciate the unique and precious nature of our home planet. Think about the role of greenhouse gases, for instance. On Earth, greenhouse gases like carbon dioxide and methane trap heat in the atmosphere, keeping the planet warm enough to support liquid water and life. But too much of these gases can lead to runaway warming, as we are currently witnessing with climate change. By studying exoplanets with different levels of greenhouse gases in their atmospheres, we can better understand the delicate balance that determines a planet's temperature and habitability. We can also learn about the potential for feedback loops, where changes in temperature can trigger further changes in greenhouse gas concentrations, leading to either runaway warming or runaway cooling. Furthermore, the study of exoplanet atmospheres can shed light on the processes that govern cloud formation and precipitation. Clouds play a crucial role in regulating a planet's temperature by reflecting sunlight back into space and by trapping heat in the atmosphere. The types of clouds that form on a planet depend on the composition of its atmosphere, the temperature, and the amount of water vapor or other condensable substances present. By studying the clouds on exoplanets, we can learn about the complex interplay of these factors, and we can improve our understanding of cloud formation processes on Earth. Imagine clouds made of silicates on a scorching hot planet, or clouds of ammonia ice on a frigid world far from its star. The possibilities are truly mind-boggling. And beyond temperature and clouds, consider the influence of stellar activity on exoplanet atmospheres. Stars, like our Sun, emit a constant stream of charged particles and radiation that can interact with the atmospheres of their planets. This stellar activity can strip away atmospheric gases, erode planetary surfaces, and even trigger chemical reactions that alter the composition of the atmosphere. By studying the effects of stellar activity on exoplanet atmospheres, we can learn about the factors that determine the long-term stability of a planet's atmosphere and its potential for habitability. Some planets may be relentlessly bombarded by radiation, while others may be shielded by strong magnetic fields. The fate of an exoplanet's atmosphere may ultimately depend on the temperament of its host star. The quest to understand exoplanet atmospheres is a challenging but incredibly rewarding endeavor. It requires us to push the boundaries of our scientific knowledge and technological capabilities, but the potential payoff is enormous. By unraveling the mysteries of these distant worlds, we can gain a deeper understanding of our place in the universe, and we can learn about the conditions that make life possible. So close your eyes and let your imagination wander to those far-off worlds. Let the whispers of alien winds lull you to sleep, and let the faint glow of distant stars illuminate your dreams. Sleep soundly, knowing that the universe is vast and full of wonders waiting to be discovered. And tomorrow, we will continue our journey together, exploring the cosmos and unraveling its secrets, one exoplanet atmosphere at a time. Good night, and may the stars guide your dreams. But the tools we use to explore these atmospheres are just as fascinating as the discoveries themselves. Telescopes like the James Webb Space Telescope, or JWST, are equipped with advanced spectrographs that can analyze the light that passes through or is emitted by exoplanet atmospheres. This light carries with it a wealth of information about the chemical composition, temperature, and pressure of the atmosphere. By carefully studying the spectrum of light, scientists can identify the presence of different molecules, such as water vapor, methane, carbon dioxide, and even complex organic compounds. It's like holding a prism up to the light of an alien world and seeing its atmospheric secrets revealed in a rainbow of colors. And it's not just about detecting individual molecules. The way these molecules interact with light can also tell us about the physical conditions within the atmosphere. For example, the width and shape of spectral lines can reveal information about the temperature and pressure of the gas. This is because the motion of the molecules, which is related to temperature, affects the wavelengths of light they absorb or emit. Similarly, the pressure of the gas can broaden spectral lines as molecules collide more frequently. By carefully analyzing these subtle details, scientists can build a detailed picture of the atmospheric structure and dynamics. Imagine, for instance, observing the transit of an exoplanet across its star. As the planet passes in front of the star, some of the star's light shines through the planet's atmosphere. The molecules in the atmosphere absorb some of this light, leaving dark lines in the spectrum. By comparing the spectrum of the star's light when the planet is transiting to the spectrum when the planet is not transiting, scientists can isolate the absorption signature of the exoplanet's atmosphere. This technique, called transit spectroscopy, has been used to detect water vapor, methane, and other molecules in the atmospheres of several exoplanets. It's like using the starlight as a flashlight to probe the hidden depths of an alien atmosphere. Another powerful tool for studying exoplanet atmospheres is thermal emission spectroscopy. This technique relies on the fact that all objects emit thermal radiation, and the spectrum of this radiation depends on the object's temperature and composition. By measuring the thermal emission from an exoplanet, scientists can infer the temperature of the atmosphere and the abundance of different molecules. This is particularly useful for studying the atmospheres of hot exoplanets, which emit a significant amount of thermal radiation. It's like taking the temperature of an alien world from millions of miles away, using only the faint glow of its own heat. But perhaps the most exciting aspect of studying exoplanet atmospheres is the search for biosignatures, evidence of life. Scientists are looking for specific combinations of molecules that are unlikely to be produced by non-biological processes. For example, the simultaneous presence of methane and oxygen in an atmosphere could be a sign of life, as these gases are typically consumed by chemical reactions unless they are constantly replenished by a biological source. Similarly, the detection of complex organic molecules, such as amino acids or nucleic acids, could be a strong indication of life. The search for biosignatures is a long and challenging endeavor, but the potential reward, the discovery of life beyond Earth, is well worth the effort. It's like searching for a needle in a haystack, but the needle is a sign that we are not alone in the universe. The exploration of exoplanet atmospheres is not just about finding other Earths. It's about understanding the full diversity of planetary environments that exist in the universe. It's about learning about the factors that determine the habitability of a planet and about the potential for life to arise in different conditions. Each exoplanet atmosphere we study is a unique laboratory, offering us new insights into the complex processes that shape planetary environments. It's a journey of discovery that expands our understanding of the cosmos and our place within it. So, as you drift off to sleep, imagine the possibilities that await us as we continue to explore these alien skies and silent storms. Let the mysteries of exoplanet atmospheres fill your dreams with wonder and anticipation. Close your eyes and allow the universe to embrace you in its infinite expanse. Sleep well and dream of distant worlds. And as we delve deeper into the study of these distant atmospheric veils, we begin to uncover not only their composition, but also the dynamic processes that govern them. We're talking about weather, but not the kind we're used to seeing on our familiar Earth. Imagine colossal storms, dwarfing even Jupiter's Great Red Spot, raging for centuries across the faces of hot Jupiters, driven by extreme temperature differences between their permanently day and night sides. These temperature gradients can create winds of unimaginable speeds, whipping around the planet at thousands of miles per hour, sculpting the clouds and distributing heat in ways that defy our terrestrial intuition. Consider also the role of exotic chemicals in these alien skies. We've touched on methane and oxygen as potential biosignatures, but the possibilities are far more extensive. Depending on the temperature, pressure, and chemical composition of an exoplanet's atmosphere, we might find clouds made of silicate, the same material that makes up sand on our beaches, or even clouds of molten iron raining down on a hellish landscape. The chemistry of these atmospheres is a complex dance of elements and molecules, reacting with each other under the intense radiation of their host stars. Understanding these chemical processes is crucial to interpreting the signals we receive from these distant worlds and unraveling the mysteries of their formation and evolution. Furthermore, the interaction between an exoplanet's atmosphere and its host star is a key factor in shaping its climate and habitability. A star's radiation can erode an atmosphere over time, stripping away lighter elements like hydrogen and helium, leaving behind a denser, heavier atmosphere. This process can have a profound impact on a planet's long-term evolution, potentially turning a once habitable world into a barren wasteland. Conversely, a strong magnetic field can protect an atmosphere from stellar winds, shielding it from erosion and preserving its potential for harboring life. The interplay between stellar activity, atmospheric composition, and planetary magnetic fields is a complex and fascinating area of research, offering us valuable insights into the resilience and vulnerability of planetary atmospheres. The tools we use to study these far-off atmospheres are constantly evolving. From ground-based telescopes equipped with advanced spectrographs to space-based observatories like the James Webb Space Telescope, we are pushing the boundaries of what's possible in astronomical observation. These instruments allow us to analyze the light that passes through exoplanet atmospheres, revealing the fingerprints of the molecules that reside within them. By carefully studying these spectral signatures, we can determine the composition, temperature, and pressure of these alien skies, piecing together a picture of what it might be like to stand on the surface of a distant world. Each new observation brings us closer to understanding the diversity of planetary environments in the universe and answering the fundamental question of whether we are alone. It is a grand endeavor, a testament to human curiosity and our relentless pursuit of knowledge, and it promises to reveal even more wonders as we continue to explore the cosmos. So, rest easy, knowing that the quest to understand these alien skies and silent storms is ongoing, fueled by our imagination and driven by the desire to unravel the mysteries of the universe. Let the thought of these distant worlds, swirling with unknown elements and bathed in the light of alien suns, lull you into a peaceful slumber. Sleep soundly, and may your dreams be filled with the wonders of exoplanet atmospheres. And as we delve deeper into the atmospheres of these distant worlds, we begin to uncover the secrets of their formation and evolution. The presence of certain molecules like water vapor, methane, or carbon dioxide can provide clues about the planet's history and potential for habitability. For instance, the detection of water vapor in an exoplanet's atmosphere could suggest the presence of oceans or other bodies of water on its surface, raising the tantalizing possibility of liquid water, a crucial ingredient for life as we know it. Similarly, the presence of methane, a gas often produced by biological activity on Earth, could indicate the presence of microbial life on another planet, though it could also be produced by geological processes. Determining the true source of these molecules requires careful analysis and consideration of all possible scenarios, a process that often involves complex computer models and simulations. Beyond the basic building blocks of life, exoplanet atmospheres can also reveal information about the dynamic processes that shape these worlds. We can observe the effects of weather patterns, such as clouds and storms, on the distribution of heat and energy throughout the atmosphere. By studying the movement of these atmospheric features, we can learn about the planet's rotation rate, wind speeds, and overall climate. Some exoplanets may experience colossal storms that dwarf anything we've ever seen on Earth, with winds reaching supersonic speeds and clouds spanning entire continents. Others may be shrouded in perpetual twilight, their surfaces hidden beneath a thick haze of aerosols and dust. The diversity of atmospheric conditions on exoplanets is truly staggering, a testament to the infinite possibilities of planetary formation and evolution. Moreover, the study of exoplanet atmospheres allows us to explore the concept of planetary habitability in a broader context. We can investigate the factors that make a planet suitable for life, such as its distance from its star, its size and mass, and the composition of its atmosphere. By comparing the atmospheres of different exoplanets, we can identify commonalities and differences, gaining a better understanding of the range of conditions under which life might arise. This research is not only crucial for our search for extraterrestrial life, but also for understanding the future of our own planet. By studying the effects of climate change on other worlds, we can gain valuable insights into the potential consequences of our actions on Earth. The journey to understand exoplanet atmospheres is a long and challenging one, but it is also one filled with immense promise. With each new discovery, we are expanding our knowledge of the universe and our place within it. The secrets of these alien skies and silent storms are waiting to be unlocked, and as we continue to push the boundaries of scientific exploration, we are sure to uncover even more wonders that will inspire and amaze us. So, close your eyes and imagine yourself standing on the surface of a distant world, gazing up at a sky filled with unfamiliar colors and swirling patterns. Let the vastness of space and the infinite possibilities of the universe fill you with a sense of wonder and peace. Sleep well, and may your dreams be filled with the mysteries of exoplanet atmospheres, waiting to be unraveled. And as we peer deeper into these far-off atmospheric realms, advanced techniques are becoming our trusted guides. Imagine, for a moment, the sheer ingenuity required to dissect the faint light filtering through an exoplanet's atmosphere as it transits its star. This is precisely what transit spectroscopy allows us to do. By meticulously analyzing the wavelengths of light that are absorbed or scattered, we can identify the unique fingerprints of different molecules present in the atmosphere. Water vapor, methane, carbon dioxide. Each molecule leaves its own telltale signature, revealing clues about the planet's composition, temperature, and even potential for harboring life. Beyond transit spectroscopy, direct imaging presents another exciting avenue for exploration. This technique involves directly capturing the light emitted or reflected by an exoplanet, a feat made incredibly challenging by the overwhelming brightness of its host star. However, with the aid of sophisticated instruments like coronagraphs and star shades, we can block out the starlight and isolate the faint glow of the exoplanet. Direct imaging allows us to study the atmospheres of planets that do not transit their stars, expanding our reach to a wider range of exoplanetary systems. Furthermore, it enables us to create detailed maps of exoplanet atmospheres, revealing variations in temperature, cloud cover, and chemical composition across the planet's surface. The data gleaned from these observations is then fed into complex computer models, which simulate the intricate processes occurring within exoplanet atmospheres. These models take into account factors such as radiative transfer, atmospheric dynamics, and chemical reactions to predict the behavior of the atmosphere under different conditions. By comparing the model predictions with the actual observations, we can refine our understanding of the underlying physics and chemistry and gain deeper insights into the factors that shape exoplanet atmospheres. It's a constant cycle of observation, modeling, and refinement, pushing the boundaries of our knowledge with each iteration. Think about the implications of discovering specific biosignatures, molecules indicative of life, in an exoplanet's atmosphere. The detection of gases like phosphine or dimethyl sulfide, which are primarily produced by biological activity on Earth, could be a tantalizing hint that life exists beyond our planet. However, It's crucial to exercise caution and consider all possible non-biological sources of these molecules before jumping to conclusions. The search for biosignatures is a complex and challenging endeavor, requiring careful analysis and rigorous validation. But the potential reward, the discovery of life beyond Earth, is well worth the effort. Looking ahead, the future of exoplanet atmospheric research is filled with exciting possibilities. Next-generation telescopes, such as the James Webb Space Telescope and the Extremely Large Telescope, will provide unprecedented capabilities for studying exoplanet atmospheres in greater detail than ever before. These powerful instruments will allow us to probe the atmospheres of smaller, rocky exoplanets, potentially including those in the habitable zones of their stars. With increased sensitivity and resolution, we will be able to detect fainter signals, identify a wider range of molecules, and create more detailed maps of exoplanet atmospheres. The data from these telescopes will revolutionize our understanding of exoplanets and their potential for harboring life. And as technology advances, we can also envision the development of dedicated space missions designed specifically to study exoplanet atmospheres. These missions could involve launching spacecraft equipped with advanced instruments capable of directly sampling exoplanet atmospheres or deploying fleets of small satellites to create a global network for monitoring exoplanet weather patterns. The possibilities are endless, limited only by our imagination and ingenuity. So, as you drift off to sleep, consider the vastness of the cosmos and the countless worlds that await discovery. Imagine the day when we finally unlock the secrets of exoplanet atmospheres and answer the age-old question of whether we are alone in the universe. Until then, let the mysteries of these alien skies and silent storms lull you into a peaceful slumber. Dream of swirling clouds, exotic molecules, and the potential for life on distant worlds. Sleep soundly, knowing that the quest to understand exoplanet atmospheres is a journey that will continue to inspire and amaze us for generations to come. And perhaps, one day, you too will contribute to this grand endeavor, unraveling the mysteries of the cosmos and expanding our understanding of the universe we call home. Good night.